Assalamu alaikum dear students. I welcome you to the 15th lecture of probability and stochastic processes. In recent lectures, we were analyzing continuous random variables using their probability density functions, PDF, or their cumulative distribution function, the CDF. We thoroughly analyzed the uniformly distributed random variable and started discussion of exponential random variable. Today we'll continue with our analysis of exponential random variables. Before we do that, let's review quickly what we learned about uniformly distributed random variable. A uniformly distributed random variable x, which assumes values between two given numbers a and b. It can take any value between a and b, including the two endpoints a and b, but all the points are equally likely. So, the PDF of uniformly distributed random variable is a flat function which is 0 outside this range a, b. It is 0 to the left of a and it's 0 to the right of b. And between a and b, it is a flat function with height being equal to 1 over b minus a, where b is the larger number, a is the smaller number. I hope you realize that uniformly distributed random variables can only exist over a finite range. If you make the range infinite and try to have a flat function with a height 1 over the infinite extent, you will have a zero function which is meaningless. So, uniformly distributed random variables are defined over a finite range of real line where they assume all possible values with equal probability. The CDF of uniformly distributed random variable is a ramp type function. It is 0 for all parameter values which are less than a. And from a to b, it rises linearly in a ramp-like fashion to 1. At a is it's 0 and at b it's 1. And for all values of parameter to the right of b, the values which are larger than b, the CDF is 1. It's very easy to find probabilities of different events for uniformly distributed random variables, because you want to find probability of an event, all you have to do is find area under PDF over the interval of real line which represents the event. And since the height of PDF is flat, all you need to do is to find the area, take the width of the interval, multiply it with the height, and you get your probability. You can find probabilities of more complicated events if the random variable is uniformly distributed, and that's also very easy. In the last lecture, we looked at parameterized conditional probabilities of a family of events. We are going to revisit that example again. Let's continue with our discussion of exponential random variables, which were introduced towards the end of last lecture, and they represent a class of random variables which assume positive values, which only take values from 0 to infinity, and the probability of them taking any value is given by the PDF, which is always of the form fx of x. The PDF as a function of x is equal to lambda times e raised to power minus lambda x. This random variable and the associated PDF defines a class of random variables, and members of this class are obtained by using different values of lambda. You can see on this slide where three such members of exponential random variables are shown. The top part of the slide shows the PDF of the three exponentially distributed random variables, and the lower part of the slide shows the CDF of the three random variables. These graphs were obtained by using values of lambda which are equal to 0.5, 1, and 2. The PDF for the random variable with lambda is equal to 0.5 is shown in red, so is the CDF, and the PDF and CDF of that exponentially distributed random variable which has a lambda value of 1 is shown in green, and PDF and CDF of exponentially distributed random variable with lambda is equal to 2 is shown in blue. You can see that if PDF is of the form lambda e raised to power minus lambda x, then CDF is of the form 1 minus e raised to power minus lambda x. You can compare the three graphs and see that for smaller values of lambda, the PDF starts at a lower height and then it slowly decays. And for larger value of lambda, the PDF starts at a higher value and then it quickly decays to 0. Similarly, the CDF for that exponentially distributed random variable which has a smaller value of lambda rises slowly towards its final destination value of 1, whereas the random variable which has a higher value of lambda rises more quickly towards its final value. These observations can be used to make judgments about the behavior of different exponentially distributed random variables with different values of lambda. The lambda is usually called intensity of failures because exponentially distributed random variables are usually used to model the failure of electronic components and other systems. So the PDF of exponentially distributed random variable represents as a function of time the relative likelihood of failure of an electronic component and other related systems like a computer server or a VLSI chip. So the probability, relative likelihood of failure of the component in the initial stages of deployment is higher and relative likelihood is lower in the later stages. But that cannot be used directly to find probabilities of different interesting events, like if the component when deployed now will survive some time, or if it is going to fail in the initial stages of deployment. We are going to use exponentially distributed random variable, its PDF and CDF, to find probabilities of such events. This is facilitated by the slide that you can see now, and in this slide you can see that we have a PDF of exponentially distributed random variable which represents the relative likelihood of failure of a television set that we have just purchased. So the x-axis is marked in months and the y-axis is relative likelihood of failure of the television set at any time after we have purchased it, and it is an exponentially distributed random variable. In this slide, a value of lambda was picked to be 0.1. That was arbitrary and it was used to just illustrate the point. So the x-axis is marked in months and the y-axis is relative likelihood of failure, and this exponentially distributed random variable has a lambda of 0.1. Hence it starts at y is equal to 0.1 for x is equal to 0, and as x increases, that is the time where we observe it if it is working or have failed, goes from 0 to infinity. The PDF goes down from 0.1 to values which approach 0. On this slide, two interesting events are defined. The first event is that the television is going to fail in the first 6 months of its deployment. So you purchase a television, put it into operation, and it is going to fail in first 6 months. The probability of that event can be found by integrating this PDF from 0 to 6. And this area under curve from 0 to 6 under this PDF is shown in red that you can see on the slide. The second interesting event that we can look at is that the TV is not going to fail during the first 2 years of service. So it's going to fail any time after 2 years or 24 months, but it is going to survive the first 2 years of deployment. And probability of that event is shown by the area which is green, which represents the tail of the PDF after value of X, which is 24 months or 2 years. You can see that for this particular model, probability of television failing in first 6 months is quite high, and probability of it surviving the first 2 years of service and not failing is quite low. You can argue that the current technology produces televisions which are much better than that, but this was just an example. If you feel that this example was kind of unfair, you can have this example compared with another example where the reliability is higher, where the intensity of failure is lower. So, in the next slide, you will see comparison of two exponential random variables. One is this one that you just saw in the slide, and the other is with a slightly smaller intensity of failure, which is 0.05. If you look at the two probability density functions which are plotted on the same axis, you will see that one lies above the other for one range, and then they switch their position and the other lies below the first one. But we are interested in those two events, that the television is going to fail during the first 6 months or the television is going to survive the initial 2 years of deployment and fail after that. This slide shows only the difference of the probabilities of these events defined for the two televisions. If you look at the slide, in this slide the red area represents the excessive probability of first television failing during the first 6 months. So red area represents the probability difference, the excessive probability of first television failing in first 6 months, because we have assumed the first television to have a lambda or intensity of failure to be 0.1, which is not very reliable, whereas the second television has value of lambda which is 0.05, which is intensity of failure, and with lower intensity of failure the second television is more reliable. So during the first 6 months, first television is more likely to fail than the second television. The difference of the probabilities of the two failing in the first 6 months is shown in red. Similarly, in this slide, the green shows the difference between probabilities of two televisions failing after 2 years or surviving the first 2 years of deployment. And this probability is the difference of second television, which is more reliable, not failing during the first 2 years, minus the probability of first television, which is less reliable, failing after 2 years. So the difference shows that indeed if we have another television with smaller value of lambda or intensity of failure, then that have better reliability. It has less probability of failing during first 6 months, and it has higher probability of surviving the first 2 years of deployment. We just discussed that exponentially distributed random variable can be used to model the survival time or to find the survival time of an electronic system from its deployment. For an exponential distributed random variable which represents the failure of electronic components, probability of this random variable lying to the right of a certain value is the survival time of the component from 0 to that value. So if the component is going to fail after a certain time t, then it's going to survive from 0 to t. So the tail of the probability represents the probability of event of survival of the component from first deployment at t is equal to 0 to the value that we are interested in. For exponentially distributed random variable with PDF of lambda times e raised to power minus lambda x, the survival time beyond t or up to t and failure beyond t is equal to e raised to power minus lambda t. Why? Remember, the CDF represents the parameterized probability of events from minus infinity to the value of the parameter. But we are interested in the probability of events which are from this parameter to infinity. So it's 1 minus the CDF, and CDF of exponentially distributed random variables is 1 minus e raised to power minus lambda x. Hence, survival time as a function of t, the time where it fails, is e raised to power minus lambda t. This problem of survival time can be made more interesting if the component has worked for some time. Suppose you have a system, a server, a VLSI chip, or a television, or any other system whose failure behavior can be modeled with exponentially distributed variable, and it has survived some time, say s. Given that it has survived till time s, what is the probability that it is going to survive a total time of s plus t measured from the initial deployment? This is a case of conditional probability. We are conditioning the probability of this system surviving a total time of s plus t, and conditioning is that it has survived for an initial time of s. We just covered that unconditional probability of the component surviving for initial time t is e raised to power minus lambda t. Now let's look at this conditional probability. The conditional probability is that given that component has survived till time s, what is the probability that it will survive an additional time t or total time of s plus t measured from the first moment when it was deployed? So the conditioning event is that it has survived till time s and it has a probability of e raised to power minus lambda s. Now the joint probability of this conditioning event and the event that it is going to survive a total time of s plus t is equal to e raised to power minus lambda and then in the bracket s plus t. And the conditional probability is obtained by dividing the two, and if you divide the two and simplify, you will get that conditional probability of this component surviving a total time of s plus t, given that it has survived for an initial time s, is exactly equal to e raised to power minus lambda t, which is unconditional probability of this component surviving an initial time t measured from the first deployment. So what's the moral of the story? If you have such electronic system whose failure behavior is modeled by exponentially distributed random variable and it has survived for a certain time, it is as good as new. If you are interested that it is going to survive for some time t, say 2 years, and if it has survived first 6 months, it has the same probability of surviving another 2 years as it had the day it was bought. So if it has not failed yet, it is as good as new. Suppose we want to apply this principle to an automobile that you have. So you buy a car at a certain date and then you use it for some time and then you think about the failure of its subsystems. For example, you can talk about the probability of survival of its universal joint, which is in the front wheel, which is popularly called in Pakistan as Goda. So you are interested in the survival time of its knee joint or Goda. So when you have bought the car and it was new, and you can say that the survival probability of this knee joint during the first 1 year was a certain value, and after 6 months, if you claim that it is as good as new and it has the same probability of survival after from 6 months to 1.5 years, and if you make such a claim particularly to somebody who is interested in buying your car and you are trying to sell the car and you are saying, look, the failure mechanism is governed by this exponentially distributed random variable, and this exponential distributed random variable, if it does not fail for a certain time, it is as good as new, then that potential buyer is certainly going to let you know about what he thinks about exponentially distributed random variable and worth of your education, particularly your knowledge of probability and stochastic processes. The point is, the exponentially distributed random variables do not model those systems which have mechanical wear and tear and other issues with them. It only models those electronic components which do not have mechanical wear and tear. So, if you are selling a car and its subsystems are working properly, don't claim that they are as good as new. They are not. But some of the subsystems which are electronic in nature can be assumed to be as good as new. This kind of behavior of random phenomena, where if it has not failed for a certain time, then it is as good as new, the probability of survival of this component measured from this time to a certain time of interest is same as the survival time measured from the initial deployment, is called the memoryless behavior. So, electronic components exhibit a memoryless behavior when we model their failure mechanism. So, electronic components, if they have not failed for a certain time, they don't remember, they don't go through wear and tear, and they are as good as new. Measured from that moment, the probability of survival for a certain interval is same as probability of the survival during the initial interval measured from the first moment when it was deployed. This memoryless behavior is unique to exponentially distributed random variables. We talked about another example when we were talking about uniformly distributed random variable, and we are going to analyze that example today to see if that random variable exhibits a memoryless behavior. And I tell you, and you should believe me, that in the class of continuous random variables, exponentially distributed variables are unique, and they are the only type of random variables which have this memoryless behavior. This memoryless behavior of exponentially distributed random variables are shown in the slide, and if you look at the slide, you will see that the top portion of the slide shows a PDF of exponentially distributed random variable with a lambda of 2, and the blue region represents that this random variable does not occur during the first 0.5 interval, the first interval which starts from 0 and ends at 0.5. So this blue region represents the survival time of 0.5, and this is unconditional probability. The lower graph shows the conditional probability of the same event, and now the conditioning event is that this random variable has not occurred for the first 0.25 units. So it has survived for parameter value of 0.25. Then what is the probability that it's going to survive a total time of 0.75? That is 0.5 plus the time it has already survived. You can see that the joint probability is represented by the red region, and the conditional probability is obtained by dividing the area of the red region with total area of red and green region. And you can see, and you can find it out with the mathematical formula of the exponentially distributed random variable, that it is indeed the case, as we move this conditioning event from 0.5 to other values, the joint probability falls, but the total probability of conditioning event also falls, and when you divide this, the conditional probability of the equipment or this system surviving a total time of s plus t, given that it has survived a total time of s, remains the same. Let's talk about memoryless behavior of other random phenomena. Suppose you enter a subway station to catch a train, and the train comes every 6 minutes, stops for a very short time. You can assume it to be a microsecond, a nanosecond, or even smaller. So it instantly picks all the passengers who needed to board and drops all the passengers who want to get down, and then it moves on. So only thing which we are interested in is waiting time, which is 6 minutes. So you enter at a random time, and it's possible that you have to wait for 2 minutes, 3 minutes, 4 minutes, up to 6 minutes. So this random phenomena of you having to wait for a certain time can be modeled as a uniformly distributed random variable. So amount of time you have to wait is a uniformly distributed random variable which lies between 0 and 6, and the PDF is a height of 1 by 6, a constant function of height 1 over 6. Actually, this random variable was analyzed in the previous lecture, and this is just an application of the random variable which we analyzed in the previous lecture. The random variable is a uniformly distributed random variable lying between 0 and 6. I'm particularly interested in the problem we discussed in the last lecture, where we said the conditional probability of this random variable lying towards the tail is what, given that it does not lie for a certain initial interval, and that initial interval was parameterized by a parameter a. We can use a, b, s, t, whatever. The interesting thing about this is that we are interested in this kind of conditional probability, that what is the probability that I have to wait for s plus 1 minutes, given that I have already waited for s minutes. So s is the parameter, the amount of time you have already waited, and 1 minute is the additional time that we are interested in. If you want to find the unconditional probability of this event, that you enter and you have to wait for 1 minute. It happens if you enter between 0 and 5. The train arrives at 0 and train arrives at 6. If you enter anywhere in between, your waiting time is the arrival of the next train. So you have missed this train and you enter anywhere between 0 and 6. So if you enter between 0 and 5, you have to wait for 1 minute. And probability of you having to wait for 1 minute at least is 5 over 6. And that is unconditional probability. Now, the conditional probability of you having to wait for 1 minute, given that you have already waited for s minutes, is a parameterized conditional probability that we dealt with in the last lecture. And this shows that this conditional probability, which is parameterized by a, goes down. When it goes down, it represents that if you have waited for 2 minutes, then probability of you having to wait additional minute is smaller compared to probability of you having to wait for at least 1 minute when you initially entered. So longer you wait, less is the probability that you have to wait much longer. So if you have waited for 3 minutes, probability of you having to wait additional minute is smaller. And if you have waited for 5 minutes, then probability of you having to wait additional 1 minute is almost 0, because in next minute the train is going to arrive. And if you have waited for longer than 5 minutes, say 5.5 minutes, then the probability of you having to wait additional minute is definitely 0, because within 30 seconds the train is going to come. Let's talk about another example of a random phenomena which could be memoryless or could not be. We'll find it out if it is memoryless. Suppose you live in a country which was founded for people who follow the best of theological principles. The founding fathers created that country so that the people can freely follow their religion, and the coming governments will make that country a welfare state where all the needs of the people will be met. The founding fathers aimed for this to happen in a certain short time, but this could not have been a certain event because there were so many unpredictable things that were going to be hindrances in the path to this realization of the dream. The biggest hurdle could be a huge number of feudal lords who were going to create states within states and prevent the dreams of forefathers to be realized. Suppose you have waited for 20 years for this dream to be realized and it has not realized yet. What is the probability that this dream will be realized in next 10 years? Is this probability larger or smaller or same when people were creating this country with this dream? It appears to be that no matter how long you wait, you still cannot be sure that this dream will be realized in 10 years. You can wait for 10 years, or you can live out your complete meaningless life and die, and still this dream may not be close to reality. Many generations may pass and still nobody can claim that this dream will be realized in next 10 years. So it appears to be that this random phenomena of realizing the dream of our founding fathers to make this country a welfare state is a memoryless random phenomena. I leave it up to you to work hard during your lifetimes and change the things fundamentally so that this random phenomena, random it may be, but it does not remain a memoryless random phenomena. So longer you work towards achieving this goal, higher is the probability of you actually achieving this goal in next 10 years or 20 years. Let's look at another class of continuous random variables which are similar to exponentially distributed random variables, but there is one difference. The PDF of this class of random variable is given by fx of x, that is PDF as a function of x is k times x times e raised to power minus lambda x. So there is an additional x to the left of exponential term. This k depends on the value of lambda, and this should be chosen in such a way that the total area under the curve is 1. So if you take this expression of x into e raised to power minus lambda x and integrate this expression from 0 to infinity. From 0 to infinity because this class of random variables also assumes values in the positive real line. So the values assumes are 0 and positive numbers. So if you integrate this expression x into e raised to power minus x starting from 0 all the way approaching infinity, you will get a value of 1 over lambda square. As I mentioned in the previous lecture, you should brush up your knowledge of differential calculus and integration because we are going to use these ideas extensively while we are analyzing the continuously distributed random variable. Anyway, so if the expression x e raised to power minus lambda x is integrated from 0 to infinity, you get 1 over lambda square. So total area under the PDF should be 1, so the k should be lambda square. Then the total area under the curve will be lambda square time the area under the expression x e raised to power minus x, which is 1 over lambda square. They cancel out and you get a total area of 1. So this class of continuously distributed random variable assume values in the positive real line, and the PDF expression is lambda square times x times e raised to power minus lambda x. The CDF is also easy to find. All you need to do is integrate from 0 to the parameter value for this PDF, and if you integrate, you get the CDF as a function of x to be 1 minus e raised to power minus lambda x minus lambda times x times e raised to power minus lambda x. So this is slightly more complicated than the exponentially distributed random variables, but they are quite similar. If you look at the slide that you will see now, there are 3 random variables of this class whose PDF and CDF are shown. The top part of the slide shows the 3 PDF functions, and the bottom part of the slide shows 3 CDF functions. As you can see, the PDF always start from 0 because of presence of the term x, which is 0 at x is equal to 0. So all the PDFs start at 0, they rise, reach a peak value, and then they slowly decay. The location and the height of the peak is controlled by lambda, and I leave it up to you to find the location and height of this peak for members of this class. Consider it a homework. The CDF rises again from 0 and reaches its final value of 1, and for those random variables which are with a higher values of lambda, they rise sharply, and those random variables with smaller value of lambda rise slowly. This class of random variables can model the inter-arrival time. Remember, in previous lectures we talked about inter-arrival times being continuously distributed, and then we also talked that inter-arrival time cannot be very small. The PDF should be very small value for small values of inter-arrival times, and it should be small for the large values of inter-arrival times. So these inter-arrival times can model many phenomena in computer science, where inter-arrival times of HTTP request on an Apache or other web server can be modeled with this type of random variable. So inter-arrival time has a small value of PDF for smaller inter-arrival times, and it has a large value of PDF for a certain value in between, which depends how popular the site is or how popular the restaurant is if we are modeling the inter-arrival times of customers. In any case, this PDF or CDF can be used to find probabilities of interesting events, like what is the probability that customer does arrive in the first few minutes, or what is the probability that customer does not arrive for first certain minutes. So this probability distribution or cumulative distribution functions can be used to answer questions like this if it is assumed that inter-arrival times can be modeled with this class of continuously distributed random variables. One important thing that we are going to look about this class of random variables is their memoryless behavior, which we will find that they don't, because we already discussed that only the exponentially distributed random variables have a memoryless behavior. Anyway, let's look at this kind of events. Suppose that we have this class of continuously distributed random variables which model the inter-arrival times at a restaurant, and we are interested in this kind of unfortunate phenomena that the customer does not arrive for next 1 minute. We can have this event as unconditional event where we open a restaurant or start measuring our observation time at any moment, and then see if the customer does not arrive during the first minute of our observation. That is unconditional probability. And then starting from our observation time, we wait for a certain time, say 2, 3, 4 minutes, and then try to get a feel that what is the probability that customer will not arrive during the next minute, given that we have already waited 4, 5, 6, 7 or 8 minutes. So these 4, 5, 6 or 7, 8 minutes are parameters. So we are interested in this parameterized conditional probability of customer not arriving in the next minute, given that we have already waited for a certain number of minutes. You can use the basic formula of conditional probability, find the probability of conditioning event, and divide the joint probability with this conditional probability to find what you are interested in. And I have calculated this and I have drawn this conditional parameterized probability as a graph. If you see this graph in the slide, you will see that the conditional probability is high for initial values and it goes down. So the probability of customer not arriving in the first minute is high, but if you have already waited for a certain number of minutes, then the probability of customer not arriving in the next minute goes down. But it does not go to 0. It goes down, then it levels off. And it levels off and asymptotically it becomes a constant value. So when you open a store or start observing your time, then initially probability of a customer not arriving in the first minute is high. Why? Because this x times e raised to power minus lambda x type distribution is small during the first part of its distribution. So probability of customer not arriving in the first minute is small and customer arriving afterward is large. So initially the conditional probability for having to wait 0 minutes, which is unconditional probability, is high. But as you continue to wait and then start your 1 minute interval, the probability of customer not arriving in that 1 minute interval, given that you have already waited for a certain number of minutes, is less. And it tapers off and asymptotically it becomes e raised to power minus 1. For this particular case, I have used lambda value of 1. So the PDF expression was fx of x. The PDF as a function of x was x times e raised to power minus x. And for this particular case, the unconditional probability of customer not arriving in the first minute is 2 times e raised to power minus 1, which has a numerical value of 0.73576. And this conditional probability tapers off, it becomes less. And as you can see on the slide, this becomes asymptotically equal to e raised to power minus 1. So the moral of the story is, if you have just opened a store, then probability of a customer not arriving in the first certain interval, say 1 minute or 1 hour, is high. But you should be patient and wait, and if you have waited long enough, say 10, 11, 12 hours, then probability of customer not arriving in the next hour is smaller, but it's not 0. If it was 0, then it was guaranteed that the customer will arrive. So this probability of customer not arriving in the 10th hour is smaller compared to the customer not arriving in the first hour, but this probability is not 0, it's just smaller than the probability of the first hour. So if you have set up a website, you have opened a store, or you have started a business, then you should be patient, because probability of customers not arriving in the first hour, first month or first year is high, and if you have waited long enough, then this probability goes low. not to 0 but to a lower value, and then probability of customers not arriving in later days, months or years is small. So as the time passes, the probability of them arriving increases. So be patient and work hard. One last thing before we move on. I assumed that this type of probability density function with an expression x into e raised to power minus lambda x models inter-arrival times. I did not claim that it does. I just assumed, and it was intuitive, that this is reasonable that this PDF could model such a random phenomena. My assumption could be wrong, and there are ways where this assumption can be verified or refuted, but those statistical methods are not covered in this course. So the purpose of inclusion of this example and the purpose of this assumption that this PDF models inter-arrival times was to illustrate a few points about how the probability theory and particularly different continuously distributed random variables work. Let's continue and look at another very important class of continuously distributed random variables, which are called Gaussian random variables. The Gaussian random variables are symmetric. They are defined over the whole real line, and their PDF is of this form, that PDF fx of x as a function of x is equal to k times e raised to power minus lambda x square. If you look at your textbook or any other source, you will see that the PDF for Gaussian random variables is given differently. In future lectures, we will switch to that expression, but in line with what we have been doing recently, we will continue to use lambda, and we will assume that we need this k to make the total area under the PDF equal to 1, and lambda is the class parameter, and by changing lambda we can have different Gaussian random variables. So for now, the Gaussian distribution is given by k times e raised to power minus lambda x square. So once again, you take this expression of e raised to power minus lambda x square and find the total area under the curve from minus infinity to infinity. This is not easy, but if you do certain mathematical manipulation and you know the relationship between repeated integrals and iterated integrals, you can find out that the total area under this PDF expression without k, that is the expression e raised to power minus lambda x square, comes out to be square root of pi over lambda. So if you take expression e raised to power minus lambda x square, take its total area under the curve, it is square root of pi over lambda. Hence your k should be square root of lambda over pi. So for now, our PDF for Gaussian random variables will be square root of lambda over pi times e raised to power minus lambda x square. By taking this expression, I have drawn three members of this Gaussian random variable class, and you can see them from this slide. In the slide, the top portion shows three Gaussian random variables with lambda values of 1, 2 and 4. The Gaussian random variable with lambda is equal to 1 is shown in red, the one with lambda is equal to 2 is shown in green, and one with lambda is equal to 4 is shown in blue. The lower portion of the slide shows the corresponding CDFs in the same colors. One important point, that if you want to integrate this PDF expression as a parameterized integration from minus infinity to a parameter value x, you cannot have a closed form solution. So from PDF to CDF, the only way to find value is numerical methods. So I have relied on numerical methods to find this CDF, and this CDF is plotted on the lower part of the screen. So top part shows 3 Gaussian random variables with lambda is equal to 1, 2 and 4, and the lower part shows the CDF for the PDFs plotted above. If you compare the 3 graphs, you can see that as lambda increases, the PDF becomes narrow. For smaller values of lambda, PDF has a peak which is smaller. The peak is at 0, it is smaller and it decays slowly. For larger values of lambda, the peak is higher but it decays more quickly. The total area under the curve remains 1. Similarly, for smaller value of lambda, the CDF started rising at a left point which is slightly to the left of other cases and rises slowly and reaches destination value of 1. If lambda is high, this ascent starts later, rises quickly, reaches the destination point of 1 quickly and then remains 1. For all the cases, the CDF passes through a point of 0.5 with x being equal to 0, which signifies that it is a symmetric distribution. The probability of this random variable having values to the left of vertical axis is 0.5. We have discussed different continuous random variables. We started with exponential distribution, and then we moved on to a slight variation of exponential distribution, and just now we started our discussion of Gaussian random variables, and the Gaussian random variables were presented as a class of random variables with distributions given by the PDF given by square root of lambda over pi e raised to power minus lambda x square. And you just saw the PDFs and CDFs of different Gaussian random variables. These random variables model very interesting and very common random phenomena, and we are going to use the Gaussian random variables to solve a few real life problems, and that is going to happen in next lecture. Till then, I wish you goodbye. Assalamu alaikum.